Представлять Михаила Хеннера, который к нам приехал из Кентукки университет. Сейчас больше
энтузиазм.
Нет, у меня никаких негативных или еще каких-то. Я просто боялся, что я засобью. Сложно. Много слов. Вот. Ну а про тему лекции Миша сам рассказывает. Я вам сам.
Значит, извините, что я буду по-английски докладывать. Это совсем не из-за того, что я пытаюсь себе цену набить. Здесь нет этого фактора. Ноль. Это из-за того, что я начал работать в этой области пару лет назад. И весь лексикон у меня исключительно английский. Я просто не знаю 99% терминов.
Боюсь, что этих 99-90 и нет.
Да, скорее всего, что так и есть. И поэтому у меня, так сказать, нет другого выбора. Ну, тогда давайте я сразу на английском перейду мягко. So this will be the intro review on modeling of growth and instabilities of microsteps on crystal surfaces. So I will try to use at least 1 hour, maybe 1 hour and a half, which I can use. So let's start with just defining what we are talking about here. On the top photograph, you see the equilibrated PB crystal, PB свинец. So this was grown by some technique like molecular beam epitaxy on a certain substrate, which is of no importance here. What you probably don't see here because of this light is that the top of this dome is a flat face. Okay, this is a face, as crystallographers call it. It looks like this in a cross section. Okay, and when it smooths down like this, becoming curved until it meets the substrate. Okay, over here. So if you zoom into the transition region from flat top to this curved sidewall, what you will see is looking like a cake, okay, layer by layer. In other words, you see here probably a collection of several steps, one on top of the other. Imagine the staircase where the steps partially overlap. Okay? So such a surface, which is actually collapsed into a point here in this sketch, such a surface is called the vicinal surface. Okay? And which is very common in crystals, not only in equilibrium crystals like this, but also most crystals grow in what is called a step flow mode, which is schematically first a monoatomic terrace is grown, okay, the height of which is 180. All right. When on top of this flat terrace, another terrace starts to appear, say at this end, okay, and when it grows in this direction, the edge of the terrace is the step, okay. Now, in this process, when it is only partially covering the bottom terrace, another terrace nucleates, and it starts to grow, featuring its own step edge, okay. And so the crystal grows like this, layer by layer, all right? This is not, of course, the only mode of crystal growth. Another mode of crystal growth is nucleation of islands. In other words, somewhere here, an island may be nucleated, all right? And on top of this island, another island may be nucleated. And so this structure may grow like a dendrite, essentially, in these directions, okay? So these represent basically two basic modes of crystal growth. the step flow mode and the island nucleation mode. Okay? So this talk will be about the step flow growth mode of the crystal.
Миша, чуть не могу понять, когда оно нуклеит, то там все равно некуда деваться, он не может создавать слои меньше, чем ему надо. То есть все равно же оно будет теми же шажками.
Нет, не будет. Это будет совсем по-другому выглядеть. То есть будет следующее. Здесь один, здесь другой, они растут, сливаются друг с другом. В это время сверху растет еще один, может быть. Да. То есть реально картинка будет совсем не похожа на то, что здесь происходит. Здесь, так сказать, это более упорядоченный процесс. Слой за слоем он растет. У меня, к сожалению, нет иллюстраций к Кайлу. Значит, здесь на этой картинке, так сказать, это so this is a schematic, okay? There is a schematic of a crystal, and then right here there is this region of a vicinal, which when you zoom into, it looks like this. You see terraces which end with curved steps, okay? The steps, of course, you expect them not to be flat, all right? So there is a certain instability which makes them curve, okay? And these steps grow and the crystal grows up, all right? This image is not really important, okay? So I will skip it. Now this is the real STM photograph from a scanning tunneling microscope. What you see here is 1, 2, and 3, and 4 terraces, okay? Each terrace ends up with a step, okay? And the step takes quite a corrugated shape, all right? So it looks like certain atoms are missing from each step. From the bottom step, like this atom is missing, all right? And certainly this is a vacancy where the incoming atom can impinge on the step and incorporate into the step and elongate the step here, okay? The second step shows several such imperfections, all right, where the atom may attach and elongate the step, and so on. So these imperfections are called kinks, all right? And so the atoms which come from terrace by diffusion are attached to the step at kinks, okay? And by this process, the step grows. Now, if we're speaking about step instabilities, when there is two types of instabilities. Number one is step bunching. So this ideally regular step train is unstable with respect to instability, which makes terraces shrink and the steps become one on top of the other, forming some macro step, okay? So this macro step may be 10 atomic heights, for instance, if 10 steps overlap, all right? Another instability is the meandering instability. This is when a step is unstable with respect to a shape perturbation, becoming some curve, okay? So this is the idealization, of course. In reality, what most often happens is that both instabilities coexist, all right? So the steps both bunch and meander. Now,
а вот этот meander, там какой-то есть период или это именно что-то такое, там типа тангенсоподобное?
Это просто картинка.
Ну, то есть там типа фингеров тоже.
Конечно, да. Вот здесь, если вы, if you look closer here, you may see the meander. Even better see it here, okay? Try to cross-sect this image horizontally, okay? And each horizontal cross-section will give you the step shape, okay? This is another one here. also meandering instability, and then one more over there. Okay, I cannot make fill the screen. Okay, now fill the screen. So this is taken from the surface of silicon. All right, silicon is the standard material. Most experiments are done on surfaces of silicon, and these images are taken from surfaces of Cu lead. This is from another silicon. Right? This you should see perfectly well. Okay. So this shows together bunching and meandering, all right? So this is the meander, all right? But right here, the steps bunch, okay, forming a macro step, all right? This is the large surface, which is maybe 10 atomic distances above this level here, okay? And right here, we are also about to bunch, all right? This is another image, okay? 3 macro steps formed by bunching of the steps, okay? And the whole macro step is curved, all right? So the goal, as you may imagine now, the goal of the modeling is to model these instabilities, okay? So I started to work in this area not long ago. I submitted one paper and published another paper on certain aspects of this complicated process, all right? And it is really complicated because you can build your model along different lines, all right? You can consider microscopic aspects on the length scales of angstroms and time scale of picosecond. Here you need to track individually every atom, okay, as it diffuses. Then you can adopt the mesoscopic perspective and describe the steps using the statistical mechanics. Essentially building the effective Hamiltonian, which involves interactions of atoms on the surface, and from the effective Hamiltonian you can find the equations of motions for atoms. And then you can work in macro world, all right, build a macroscopic model where you formulate continuum equations. So this is what this talk is about continuum modeling using partial differential equations. The most fancy approach these days is microscale approach, where you combine elements from each length and time scale, okay? And you feed up the information from smaller length and time scales into the equations on a macro scale, into the partial differential equations. But this is a complicated model. I'm not doing this so far. So now here, before we start to model anything, we need to idealize our problem, right? So you start sketching something like shown in this figure, okay? You have 2 terraces. The top terrace, which is shaded, is this terrace, and the bottom terrace, which is white, okay? And when atoms diffuse on both terraces, all right, and they attach to the step at kinks that you have seen in this STM photograph, all right? Now, look now at this bottom picture, which shows possible atomic motions, okay? What can happen with the absorbed atom after it arrives from the vapor phase or from a molecular beam onto a terrace? Where can it diffuse? Number one, if it arrives on the lower terrace, which can diffuse toward the step, which acts like a sink for atoms, and where it directly attaches to a kink. Okay, this is the A error. Okay. Number 2, it can detach from a kink. If it has sufficient energy, it can detach from a kink and go onto the upper terrace and then disappear from the picture, go away from your step. Okay. Number 3, it can, if it is energetic enough, it can come from this direction and cross the kink. Because it has too much energy, it does not attach to the nearest kink. It crosses the kink, goes over here, and then probably attaches to another kink after it loses some energy. All right. So this is the kink crossing process. Then 2 atoms arriving from the lower terrace can arrive to the step, come together, and nucleate a dimer. All right. And this dimer may attach to the step. Okay. So this describes basically processes on the lower terrace. All right. Now what about the upper terrace? The atom coming to the step from the upper terrace, if it is very energetic, it can jump over the step, okay, and then continue moving until it goes away from the step. So this atom does not attach to the step. Then there is another 2 processes which unfortunately are not shown here. One is it goes over the step, but then, because the step is a sink, it goes back and attaches to the kink. Okay, so it goes like this. All right. And the third process, it arrives to the step, but because at the step there is a potential barrier for the atom to go over, which is rejected by the step and it goes back. Okay. So there is a number of processes as far as atoms motion here, which must be incorporated in the model. All right. Some of these processes are high probability, like attaching to the kink. Other processes are very low probability. All right, like step crossing. It's a very low probability process because atoms must be very energetic to cross the step. Right. And next, the upper right picture is the continuum approximation of this discrete. All right, so we approximate the step by a smooth curve. All right, by a smooth curve, which has a certain normal at each point, which makes the angle theta with respect to the z-axis. All right. And on each terrace, we introduce the concentration of a data field, all right? And this concentration field must be computed or calculated. And through diffusion, the atoms arrive to the step, and these quantities, J plus and J minus, symbolize the fluxes, diffusion fluxes to the step. And this is the diffusion flux along the step, okay? This corresponds to this KC process, okay? Where atoms diffuse along the step and then attach somewhere, all right? Now, the next picture, the next 2 pictures actually, they are actually variants of a single picture. They just complement each other. They show symbolically that atoms arrive to the terrace from either vapor phase or from the atomic or molecular beam. F is the flux, okay, the flux to the terrace. Then they diffuse on the terrace with some diffusion coefficient D. Then they attach to the step from either the lower side or the upper side. If this atom is able to jump from the step, then it can attach here. And the rates are respectively nu plus and nu minus. And nu minus stands for the, let me show this picture again. So the upper terrace has the index minus. the lower terrace has the index plus, okay? And this is how it will be always. So in this picture here, the attachment rate from the upper terrace is mu minus, and the attachment rate from the lower terrace is mu plus. Then they diffuse along the step with some diffusion constant dl, okay? And also they may desorb back into vapor phase if the temperature is high enough, when not all of them remain on the terrace. Some of them will desorb back. Okay? What this picture adds to that picture, it adds this potential barrier for the atom to jump from the step when it arrives from the upper terrace. Okay? This potential barrier height is maybe 10 electron volts. All right, so it's really tiny, but it is enough to repel most atoms which arrive to the step from the upper terrace. All right, so the majority of atoms, the vast majority, attach from the lower terrace. And then also this picture shows the coordinate system, the z-axis in this direction and then the x-axis along the step. Okay? So far we have considered a single step basically, right? But the next picture so this one shows the real situation which needs modeling, all right? You have a train of steps. All right, several steps, maybe 10, maybe 15, any number, n steps. On each terrace between the steps, there is its own diffusion field. Okay, the atoms go as I described. All right, attach, detach, cross, whatever. All right, and so this is a collective dynamics of n steps that you need to model essentially. All right, this is the advanced modeling, which I will not be discussing at all in this talk. I will be focusing on a single step, separating two terraces. Okay? But the models for n steps do exist. They are complicated, but they do exist at this point. So this is just a list of references. I took these pictures from these papers. I can send this list if you are interested in learning more. Okay? And so now I'm smoothly transitioning to the main part of my talk, the modeling. Okay, let's see. I will make it full screen. Right. So I'll skip the first two slides because they repeat what you have seen. All right. So this is the first slide that we need to discuss. So first, we need to introduce some aspects of equilibrium thermodynamics. Okay, define some quantities which will appear later. All right. So number one, let a function gamma of theta, where theta is the angle of the normal to the step. Picture again the step, which has a normal pointing into the lower terrace. And this normal makes the angle theta with the z-axis. Okay? So let this gamma of theta be the step energy. Often it is called line energy, or step tension, or line tension. Essentially, this is the analog of the surface tension which we are used to in fluid dynamics. But the key difference is that surface tension of a fluid is a constant, okay? It is independent of orientation, while this is dependent of the orientation, okay? And then, if we integrate this function along the step, all right, when we obtain the energy of the step, called free energy in thermodynamics, all right? This is the line integral, as we know it from calculus. If we now pass from the arc length s to the variable x along the step, then you get this integral, okay? Where theta of x is simply arctangent of the slope. if you describe the step by function h of x and t. Okay? So next, if you add or remove an atom from the step, then the change of this quantity is the step chemical potential, and it is calculated by taking a variational derivative of E with respect to H, okay, and multiplying by an area where an area is a constant. It's the area occupied by a surface A. All right. If you do this calculation, which is not that difficult, then you will get that the chemical potential is the curvature of the step times gamma plus its second partial derivative. Actually, it's the ordinary derivative because gamma is a function of theta only. So gamma plus its second derivative, all right, which is denoted as gamma tilde, which is called the step stiffness. Okay. So basically, where in fluids you have surface tension, in solids you have surface stiffness. Okay, and which is orientation dependent. All right, it's not a constant. So the chemical potential will feature in the following derivations. All right. Next, in the next 4 slides, we will formulate the step dynamics as a moving boundary problem. All right. There will be 4 slides total, and a summary slide where all equations will be listed together. So on each terrace, we formulate the diffusion equation for the concentration of atoms. Okay? The diffusion equation certainly has at its left side the time derivative of concentration, when it has the Fickian term, the diffusion term, where d is not a constant. In general, d is the tensor because atoms have different probabilities of diffusing in different directions along the surface. Along some directions it's easy to diffuse, along the other directions it's difficult to diffuse. So diffusion is anisotropic, okay? Therefore you have the divergence of this product, all right? F is the incoming flux of particles, of atoms to the surface, and this is the desorption time, all right? Tau is the mean residence time of atom on a terrace, all right? Next important piece is what is called the quasi-static approximation, all right? So basically, in a nutshell, it is absolutely legal to ignore the time derivative at the left-hand side, okay? And the reasoning is shown here. All right. If you combine your dimensional quantities into the velocity of a step when there is only one combination, all right, which the dimensions allow, it's this combination: f times the surface area of atom times the typical distance between steps. When you can define the speed of atom diffusing over this distance L, and certainly if V is much less than Vd, then you can ignore the left-hand side, okay? It's 0. And this is equivalent to L being much less than this quantity, okay? And it turns out if you plug the values of these 2 parameters, then the right-hand side is quite large. And what happens in practice is that steps nucleate at distances which are much less than this value, okay? So it is always legal to work in the quasi-static approximation. Basically, there is some exotic situations where this quasi-static approximation fails, and one of these situations is the step crossing, all right? I can go back. It's this process, all right? When steps are transparent, as we say. This is the jargon, okay? When steps are transparent, then quasi-static approximation is no longer valid, and you need to include the time derivative, all right? But we will be omitting it, okay? Next piece of this model, you formulate the constitutive relations essentially you define the fluxes J plus and J minus from the lower terrace and from the upper terrace, all right? And these fluxes have this form, all right? The main pieces are this and that, okay? So each flux is proportional to concentration difference, where C plus is value of the concentration field exactly at the step, okay? And this thing, which depends on the chemical potential, is called the equilibrium concentration, and it will be explained on the next slide, all right? And so this difference is multiplied by the attachment rates, mu plus and mu minus. And the chair number 2 is the step crossing chair, okay? Step transparency chair. We will zero this chair, ignore it, okay? This is the typical situation. Most often it is irrelevant, all right? And when this equation defines the diffusion flux along the step, okay, going back, it's this process when atoms diffuse along the step, all right? So this flux is proportional to the derivative with respect to the arc length of the product of the chemical potential and the mobility function. The mobility function is an isotropic. It depends on the orientation at each point of the step, okay? The expression for the chemical potential is here, okay? So this will be plugged into care when the derivative is taken and you have then the usable form of J sub F, right? And now what you do with these things, the step moves in response to the net attachment current as well as due to this mass transport along the step, all right? So you can write that normal velocity of a step is this expression, okay? Sum of these two fluxes, and you need to subtract that flux from here. And now I simply plug the expressions, this and that, for J plus and J minus, and I got this form, all right? After you have formulated the normal velocity, it's easy to obtain the equation for the shape, h of x and t, which we will do, all right? Now, let's explain this equilibrium concentration, okay? This is another thermodynamic concept related to the step energy or step tension, whatever you like to call it, okay? So basically, this is the manifestation of the thermodynamic driving forces that are responsible for restoring equilibrium at the step, all right? Basically, how to explain this? Imagine that the step forms a bump, okay, like this, with a positive curvature, all right? Then your step tension, just like the surface tension of the fluid, pushes the step back, all right, by sublimating atoms from the step. So if you want to preserve this bond, if you don't want it to dissipate, all right, when you need to keep a higher concentration at the bond. And this is what this formula establishes, all right? Look first at this expression. CEQ0 is the equilibrium concentration of a straight step, all right, a straight step. And then which is multiplied by this positive quantity. Mu is positive because curvature is positive, all right? So for the curved step, where the concentration there must be high, all right? And this expression is just the Maclaurin series expansion of this form, all right? Where it is assumed that mu is much less than what Boltzmann constant times the temperature, all right? So this is what we will plug into our formulas for CEQ mu, okay? This quantity is dependent on the orientation, right? Because mu has a certain stiffness image which depends on orientation, and which is proportional to curvature too, right? Next, and this is the last part, the mass conservation at steps, all right? This is clear that the fluxes at the steps are written like this, all right? The scalar product of d times gradient of concentration precisely at the step and the norm. And this one is with the negative sign because the normal points into the lower terrace, all right? And here n is the same, so we must have the negative sign. And so now if we zero in the permeability, the step crossing, if we combine equations, if we plug this equilibrium concentration and the chemical potential, then we will get two Robin-type boundary conditions for the concentration fields at the step, all right? This is the boundary condition for the concentration field on the lower terrace. And that is the boundary condition for the concentration field on the upper terrace. Okay. Here we introduced the gamma, which is basically the dimensionless step stiffness gamma tilde. So gamma is not a constant; it's orientation dependent. Okay. And now this is the summary. All right, the summary. On two terraces separated by the step, we have this equation, one for each terrace. All right. F is a constant, so it's the inhomogeneous partial differential equation for the field C, which depends on x and y. Okay. We have two Robin-type boundary conditions, all right, for each of these equations. One for each of these equations at the step, okay? And when we have the motion law for the step, remember we wrote the expression for the normal velocity, it was this, okay? And when the normal velocity is simply connected to the time derivative of the shape function, okay? ht over cosine of theta. And cosine of theta can be expressed through h sub x, through a slope. Right? So this will give you a partial differential equation for the dynamics of the step shape. All right. Okay. All right. So probably I will skip this slide. It's not very important. So now imagine that you take this free boundary problem and you do a linear stability analysis of a straight step. Okay, so you want to figure the conditions when this straight step loses its straightness and becomes curved. Okay. Basically, what happens is, in a nutshell, like this. If the incoming flux F is less than this quantity called the equilibrium flux is less than this quantity, then the desorption from the terrace overcomes this flux and the step doesn't grow. Okay, so the step stays where it has nuclei, it does not enlarge. All right. If you increase the incoming flux above this value, then the step starts to grow. Okay. And if you increase the flux even more to be above this value here, okay, when the step loses its straightness, not only it grows, but it becomes curved as it grows. So you have the meandering instability for values of the incoming flux larger than that. All right. Now, physically, what drives this instability? All right. What is the physical mechanism? The physical mechanism is basically shown in this picture right here. Okay, if the step is curved, then the isoconcentration lines on the lower terrace become compressed near the peaks. Okay, what this means is that the flux here becomes larger. All right, if the flux is larger, it certainly increases this perturbation here. All right. But when perturbation increases, it compresses the isoconcentration lines even more, which increases the flux more, which drives this instability more. So you have this positive feedback, okay, positive instability feedback. If you ever heard about the Martin-Seketa instability in solidification phenomena, then what goes on here is the precise analogy of this. Okay. Now finally, what we are going to do in the next couple of slides is to formulate this evolution equation for the step shape. All right. Non-linear PDE which governs the function h of x and t. All right. We will make a number of simplifications of this full three-boundary problem that you have seen. We will assume infinite barrier from the upper terrace, so that atoms that come from the upper terrace will never jump onto the lower terrace. All atoms are rejected by the step and go to infinity all the way behind my back. If in front of me is the lower terrace, behind me is the upper terrace, the atoms that come from this direction are rejected by the step and go back. So this mu minus attachment rate is 0. We assume non-zero desorption, okay, which is always non-zero if the temperature is sufficiently large, and which is always sufficiently large. We assume isotropic diffusion, all right, so that D is just a constant. We will neglect diffusion along the step, all right, mass transport along the step, so that GE, which was actually labeled as G sub L in the previous slides, is 0, all right. This eliminates this contribution, okay, from the normal velocity. Finally, we will make absolutely unrealistic assumption that light energy, or step tension, whatever we like to call it, is isotropic. Okay, so parameter gamma, which you have seen in the equations, this parameter here is just a constant. Okay? And so when the problem for a single lower terrace, now we have eliminated the upper terrace completely from consideration, so that we have now only the lower terrace, okay, the lower terrace and the upper terrace is irrelevant, all right? So on this lower terrace, you have the static diffusion equation, all right? Where at infinity is over here, the step is assumed infinitely long, okay? At infinity, you fix the concentration field, all right? And the physical value of concentration there is the product of tau times F. So at infinity on the lower terrace, the concentration is fixed. Then at the step, we have the normal velocity, which takes this form in the reference frame moving with the step. We don't know the velocity yet of the straight step, but we split it out. V0 is the velocity of the straight step, of course, the step is not straight due to instability, but this velocity of a straight step can be calculated through the solution of this problem. All right, and we will show the expression for this. Chance cosine of theta, and this equals to the flux essentially. Okay, this is the incoming flux. All right, and then also at z equals h of x and t, we have value of c fixed. All right, c is this product, where k is the curvature. All right, so c is different at all points on the step because curvature there is different if the step is step. All right, m is the normal vector. And cosine of theta in the normal vector is this quantity expressed for the slope hx. Okay? And when you do a linear stability analysis of this problem, first you notice that it has the basic state, which is the straight step. All right, h of xt equals 0, and it is 0 because we are in the frame of reference moving with the step. Okay. So h is 0, and this velocity is this expression, which is proportional to the difference between the equilibrium flux and your real deposition flux. All right, and also a part of this basic state is the concentration field of this lower terrace. So on the lower terrace you can solve for the concentration field exactly in the basic state, and it is this function which basically shows you that the concentration field decays from infinity, where it takes value tau f, to a step exponentially. All right. If you check here z equals 0, which corresponds to where the step is, then you will have this will be 1, tau f, and this tau f will cancel, and at the step you have concentration CQ0, as you should. Remember the discussion of the equilibrium concentration. At the straight step, concentration is CQ0. All right, and when we do a regular linear stability analysis of this basic state, and you come up with this growth rate of a perturbation, all right, and it turns out that when this parameter is less than 1/2, and this condition corresponds exactly to the one that I showed before, it can be written in this form, all right, where f is larger than this fc, okay? So when f is larger than fc, then omega is positive, all right? So the growth rate is positive, you have the long wave instability, and you can calculate the cutoff wave number, all right? All right? And finally, after you have done the linear stability analysis, you can do the weakly stability analysis and obtain the nonlinear dynamics of the step. So you probably should be very familiar with this, at least I know that Seryoja is. So near the stability threshold, you introduce a small parameter which is equivalent to a departure from the threshold, okay, R. It's epsilon, and then you introduce the long wave variable, capital X, and the slope time, capital T, and you scale the step profile like this, which means that deformations are allowed small. Okay? Step deformations are order epsilon to 1. When you expand the concentration field and the position of the step in these power series in epsilon, okay? And you plug in these expansions, solve the problem at each order, and at the third order, you obtain the Kuramoto-Sheveshinsky equation for the profile of the step, all right? This is this celebrated equation, and here, just the meaning of these variables is shown, okay? So this x here is actually your long weight variable capital X times this square root, and h is actually this dominant contribution to the h here, okay? And the t here is related to the slow chime, all right? It's essentially the slow chime that chimes the numerical parameter. So to summarize, the dynamics of your single step when you ignore the upper terms obeys the Kuramoto-Sheveshinsky equation. Now a few words about the Kuramoto-Sheveshinsky equation, which is a complicated equation because it features the spatial temporal chaos. Without going in details, if you do a linear stability analysis of this equation, this is very easy to do. Just check h equals a constant plus perturbation, plug in here linearizing perturbation, check normal modes. If you do this, then you obtain the maximum growth rate of a perturbation, which is this value, 2 times square root of 2 times pi, approximately 8.9. And now imagine that you are simulating this equation numerically, all right, on some domain of length capital L with periodic boundary conditions at the left boundary and the right boundary. Okay. So what happens is that if you check the length of the domain, any value between 0 and 2 times the maximum wavelength, then if your initial condition is just a random noise, okay, then this random noise develops into a periodic solution, all right, into a periodic solution, which translates in the z direction with some positive velocity because the step is growing, okay, and this speed is this, okay, the speed of a straight step, which you know the expression for this, okay, times actually plus this quantity, which is the spatial average of hx squared. Right? But now, for L any value between 0 and this, you get a periodic solution no matter what. Okay, step is regular and periodic. Right? Okay. And propagates in this direction because the flux is from here. But if you check L larger than 2 times lambda max, then your random initial condition develops into chaotic solution. All right, and here is 2 computations taken from different sources. This one is probably not that obvious, but this one you can see that there is no regularity here. If we closely zoom, and it's actually chaotic. Right? So I have done today what I wanted to do. All right, I did this. Introduced the thermodynamically consistent model of the isolated step growth. All right. So I took a single step, all right, and modeled it. I introduced all the necessary constituents, all right, from thermodynamics. I derived the Kuramoto-Sheveshinsky equation, which governs non-equilibrium, which is when the incoming flux is above the critical value. And so what I'm going to do in the next lecture is 2 different problems, not related. Okay. Number 1, in this discussion, the step tension was approximated by a constant. All right. So I want to discuss the effects of the step tension anisotropic, dependent on orientation, as in real life. Okay. This anisotropy can be weak or it can be strong in a certain sense. Okay, and I'll define precisely weak anisotropy and strong anisotropy, and the modeling will be different. All right, for weak and strong. And the second problem which I will discuss, if I have time, actually I don't know which one I will start with, this range, I cannot yet decide. But the second problem it will be growth of the step with anisotropic but weakly anisotropic energy, which is relatively simple. But what drives the growth is not just the deposition of atoms on a step, on a terrace. What drives the growth is the deposition of molecules on a terrace, as happens in the process known as chemical vapor deposition. In this process, the molecules arrive to the terrace, and once they arrive to the terrace, they crack, releasing the atomic constituents. So a molecule may consist maybe of 2 or 3 or 4 atomic constituents, depending on the complexity of the molecule. And when these constituents diffuse separately to a step, and the relevant ones incorporate into the step, and the step grows. Okay? So I will discuss this problem when the molecule cracks into 2 different atomic species, which diffuse to the step. All right, and I believe one of them incorporates. Okay. Now this is just the list of some advanced topics for which there will be no mention. All right. Meandering bunching and meandering bunching in a step train. So not just a single step, but a train of steps. And you allow not only the flux from the lower terrace, but you allow the flux from the upper terrace as well. All right? And then these can drive the bunching of steps in addition to meandering. All right? One can think of the external fields which drive the diffusion. For instance, if you apply the voltage difference to this edge of a system and that edge of a system, then this electric field will drive the surface electrons along the terrace, and these surface electrons will scatter on surface atoms and push them in the direction you want. You may push them in this direction, away from the step, or you may push them in that direction to the step. Okay? So this way you can provide the additional external flux, all right, of atoms to the step. And then finally, you can, of course, include the noise effects. All this was deterministic in the sense that there is no noise. But of course, the temperature here is high enough, like 650 degrees centigrade. So there is a certain thermal disorder in the system. And you can incorporate this thermal disorder by including the noise term in your governing equation, for instance, in this equation here, and the noise term. Then it becomes very complicated because statistics come into play. All right. So again, this is the list of references. All right. If you want to learn a little more than I said today, then you can download this reference. It's easy to do. This can be obtained instantaneously and read it. It's absolutely readable. And then you can get probably a better feeling. Second reference is the review from Reviews of Modern Physics, dated 2010. So this contains all kinds of issues, right? Part of which are also very, very readable. And then this paper is one of the first papers where the stability analysis of a single step was done. It's very detailed and nicely written paper. That paper discusses the anisotropy of the step energy. So this one is probably of lesser importance for you. Okay. So now this last slide it refers to the issue that was raised. We disregarded the step crossing. Remember, we disregarded this effect. All right. Step crossing is also called step permeability or step transparency. Because we disregarded this when we were able to work in the quasi-static approximation, which is a huge simplification, all right? Because it's much easier to solve the elliptic PDE, this PDE, the elliptic PDE, rather than parabolic PDE, okay? Essentially solving this subject to these two boundary conditions after you separate variables boils down to solving an ODE in Z direction. Okay? So to find the field C, you simply solve an ODE, boundary value problem, all right, with boundary condition at infinity and boundary condition at a step at this location. All right. If you have the time derivative here, then it's way more complicated. So this last slide, I just copied the abstract. It says that in the case of significant transparency, the velocity of a given step in a given moment is affected by atomic processes which took place at rather distant terraces in rather earlier moments. The reason is that an atom needs time to cross many terraces before attaching to a key position. That is why the theory of crystallization with non-local kinetics should account for the time dependence of the atom concentrations on the terrace. Okay. And so in this paper we consider this, and you can see that this is a very recent paper. Only in 2009 we became interested in such problems. All right. And 99.9% of research is in quasi-static approximation, including mine, right? Okay, so I don't know how well I explained all this. I tried my best. Any questions? Спасибо. Теперь я могу говорить по-русски.